Welcome back to ECE 220, if we can find our bearings. This week I'm hoping that you will watch the PSpice tutorial, and there's also a homework assignment that you will be responsible for next week. You might want to have that with you as you're watching the tutorial. It might help you understand what's going on, and I think the tutorial steps you through at least the first half of that homework assignment, so that you should be able to sort of copy along or follow along and perform the PSpice homework assignment that's due in class next Friday. This Friday, office hours are going to be modified. They're going to be shifted 1 hour earlier so that I can go to something else that's starting at 11. Lab number 0 starts next week, and I've tried to put something together for the TAs, and I've now posted this on the D2L website, but this might help you if keep track of what section you are in and when you attend. These are the attendance schedules of your particular section. Question? I'm going to ask the TAs after class. I do not believe there's any pre-lab. The question was, is there a pre-lab for the orientation lab? That's lab 0. I do not believe so. If there is, I'll let you know tomorrow, and we'll give you the information for that on the website. And I think what I guess I could do a show of hands. On the website, I was thinking of squeezing in the labs sort of as they occur, but obviously they're a little bit out of sync. But I thought I might put a module for lab 1, another module for lab 2 in terms of the instructions for pre-lab and lab. Or do you want me to just create one module and have lab 1, lab 2 accumulated or deposited in that one module? Single modules. How many think a single module for each unique lab? Although it's really probably only going to be one link, maybe, in each module. Would that be helpful? Show of hands. How about the other way? Just creating one module and putting all the labs in the one module. I think that wins out. So I may just try to put one module in D2L that says lab material, and then you can go there to find lab 1, lab 2, etc. That's probably cleaner. And these are now when you need to show up. Obviously the pre-lab is going to be due prior to that on the Friday, and the lab reports will be after your lab. Well, everybody's lab reports are due on the same day, as are your pre-labs. And the lab reports are due the Wednesday following the week that you had lab. That, I think, is written in the schedule in that spreadsheet form before. That tells us, or gets us, a little bit more information on labs. Homework number 2 is due Tuesday. PSpice homework is due then that same week on Friday. And exam number 1, which squeezed in front of lab number 1, will be homework number 3 and maybe even 4, but homeworks 1, 2, and 3 will be the content for exam number 1. I don't know how much you are going to the website and looking things over, but after class last time, I squeezed in some additional work, and I posted that on the lecture notes for yesterday's lab, and that deals with example number 5, which I've now just cut out, and I wanted to tell you that it's now available to you to examine, and if you have questions, please let me know. But this was the KVL with an air gap. The air gap actually is associated with the voltage between these two highlighted nodes. And so you could think of that as some voltage drop between the top node and that bottom node. You can see that I've then formed two different KVL equations, a red one and a dashed black one, but they're both counterclockwise. They're both in the same direction, and that is important as you look at the combination of those two so that you can get rid of the two variables, the unknown variables that you will end up with. You'll end up with an I, the current, as an unknown, and V sub m as an unknown. You'll then need to solve those two equations in two unknowns to solve for the Vm, or that's the way that I solved it. And this ideal voltmeter, the leads in an ideal voltmeter do not draw any current or do not have any current through them. And that's why I've tried to label those as zero current. You don't have to worry about the impedance or the resistance that voltmeter presents to the rest of the circuit, which in fact it does. Taking a measurement does impact the system. This is an ideal voltmeter. In the lab, usually you can consider your voltmeter ideal, but in Chapter 3, which is what we're starting today, we will try to understand a little bit about the internal workings of a voltmeter and how that might be accounted for when we are taking measurements. But I wanted you to, and here you should be able to very quickly see what the KVL equation for KVL1 is. Relative to I, which is circulating in a counterclockwise fashion, we have 10I plus 6I plus whatever that resistor is at the bottom, 2I minus 9, and then we zip up through the air gap, minus V sub m, plus 2V, and then we're back to where we started, so all of that needs to be 0. That's KVL1. KVL2, if we start up in the upper yellow highlighted node, we would then see plus V sub m plus 2I. I is still going through that series network, minus 3I plus 4I equals 0. That's KVL number 2. Then you have to play with those, and that's in the notes for yesterday. You'll end up with an A and a B equation. You can now solve those simultaneously, or it really, in this case, makes more sense to just add them since you have a minus V sub m and a plus V sub m in the respective equations. Adding those two equations removes V sub m, gives you one equation in terms of I. You can solve for I. It ends up being 1/3. V sub m from B says that's minus 3I, and you can use your I result to end up with the measured voltage on that ideal voltmeter is minus 1 volt. You might look at that if you haven't already. I don't know how much you go home and study the notes from the day before or the day of, but I wanted to let you know that there was some additional material provided to you after yesterday's lecture, and that may occur on a common basis. Today what I want to do is move into Chapter 3, which is really combining resistors and doing voltage division and current division, and then working with other ways of measuring systems. We'll talk about the movement in a voltmeter, the D'Arsenval movement, and we'll talk about a Wheatstone bridge in Chapter 3. Today we're going to try to look at series resistors, parallel resistors, and we can solve those based on what we already know. Ohm's law, KVL, and KCL. We can start understanding how we might be able to simplify the analysis of a circuit by combining these resistors, however they are connected or interconnected in a network that we have to analyze. We'll talk about series parallel. Then it's common to combine two parallel. We'll derive the formula for that. We'll simplify some resistor networks. Maybe we have a voltage source and just a tangled web of resistors connected to that. And so far we're not into chapter 4, which tells us how to analyze a multi-node circuit, but we'll be able to simplify that network of resistors as long as the resistors are not in some weird configuration, which is a delta and a Y, and that's at the end of chapter 3 that we'll learn about. How do we convert between a delta and a Y configuration? That not only will be used in this class, but you'll also use that in the next class, 320, when you're talking about power. You might have sources. In a large power system, how many were in the ECE building yesterday about noon or a little after? It went dark, did it not? For about an hour and a half. So something was messed up with the power. I still have to find out what that was. But in 320, you'll learn how not to mess things up with power. And that's the class following this. But a lot of times you're dealing with three-phase systems. And those systems might be interconnected in a delta configuration or a Y configuration. And we're going to get the foundational material for that in this class. In that class, you'll be worried about complex impedances. Here in chapter 3, we're dealing with real impedances, real R's. But we might throw in some complex numbers just to get us sort of feeling comfortable with that so that we can do that at the end of this class, where we will talk about analyzing circuits with complex numbers, not just real numbers that we're using now. We'll then look at a voltage divider or voltage divider circuits. I want to then make sure it's clear when that technique or strategy is applied. So I'm giving us a caution, and if you want to look at that from another perspective, that's provided in example 3.4 of the textbook. We'll then get into current divider circuits, or how does the current divide when we have one current and it meets a fork in the road. Here's one branch with a resistor, here's a second branch with a resistor. How much current goes one way and how much goes the other? Let's talk about combining series resistors first. And here what we're trying to do is simplify our analysis. Meaning, we might want to, instead of dealing directly with circuit A, we might want to rewrite it into an equivalent circuit with an equivalent resistor, R equivalent, which is circuit B. And if we're doing that, then we have to be able to find this equivalent resistor. What is R equivalent? How do we write that if we know that we have the circuit A or the circuit on the left? And we can do that using the strategies that we've already learned. If these have to be equivalent, we're giving them the equivalent voltage supply. What's another variable in that circuit or those two circuits that have to be equal if these are equivalent representations? So now the answer was the bottom line. I don't know how many heard that, but R equivalent is just the sum of R1, R2, R3, and R4. We can derive that result based on knowing that, or using the techniques we've already learned. One is these are both series circuits, so the currents are the same, or the series resistors share the same current. In this case, whoa. the current I is the same through all resistors, R1, R2, R3, and R4. If the circuits are equivalent, the I in circuit A better be the same as the I in circuit B, if those two are supposed to be equivalent networks or circuits. So what's KVL for circuit A? This is just basically a warm-up exercise for what you've already been doing, right? This should be second nature at this point, writing a KVL equation for that series circuit on the left or for circuit A. Starting, let's say, in the lower left-hand corner, what's KVL in terms of V, R's, and I? And let's consider voltage drops. What do we experience first going up through the voltage source V? That's a negative drop, is it not? So there's minus V plus R1I plus R2I plus R sub 3I plus R sub 4I is equal to 0. All of those from Ohm's law. And once we go through that last resistor from right to left, we've now arrived back at where we started, and we said any complete path, the voltages sum around that complete path to equal 0. The algebraic sum. This now says that we can say R1 plus R2 plus R sub 3 plus R sub 4 I is equal to V. And in circuit B, that KVL is fairly clean. That's minus V plus R equivalent times I equaling 0. We can solve that consistent with what we just wrote down before, and now if those two equations have to have the same voltage and current associated with them, what's in parentheses in the top equation has to equal R equivalent, and that's what we said to begin with. I is the same in both circuits as long as R equivalent is equal to R1 plus R2 plus R3 plus R sub 4. And that's what was communicated at the beginning of this exercise. R equivalent is just the sum, so series resistors add to obtain R equivalent. And our general formula, if we have capital N such resistors connected in series, we just add them all up to obtain our equivalent resistor. And that might be easier to analyze. We just add up all the resistors, then we just divide by that one number when we want to find the current in that series connection. What about parallel resistors? Suppose we have this configuration, circuit. All of these resistors see exactly the same voltage across them. Is the current the same in each of those resistors? Not necessarily. We haven't said what any of the R's are equal to. And we might then want to keep track of those currents in the vertical branches. Or somebody might be interested in what's the current being supplied by that voltage source. And using KCL, we know that the sum of the currents in equal the sum of the currents out. And for circuit I, we now can say that I is equal to I1 plus I2 plus I3 plus I4. That's simply KCL. But we can write that in terms of the voltage source. Each of those I's, I1 through I4, I can also be written as V over R1 plus V over R2 plus V over R3 plus V over R sub 4. That's just applying Ohm's law. Or we can factor the voltage out, and we now just have this sum of reciprocals of those parallel resistors times the voltage source, giving us I. If we compare then circuit C with circuit D, if that's to be an equivalent circuit, then we would want this I to be the same as the current I coming out of the voltage source in circuit C. And this equivalent circuit, circuit D, is a direct application of Ohm's law. V is equal to R equivalent I. Or, solving for I, we can say V over R equivalent, or 1 over R equivalent times V. Now, when you see resistors in parallel, you might be thinking about standing on your head, right? Now everything's reciprocal. We now have this 1 over R equivalent is equal to the sum of these reciprocals. So if I is the same in circuit C and D, then that's requiring 1 over R equivalent to equal 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R sub 4. Or, stating that, we can say that parallel resistors combine by adding reciprocals to obtain the reciprocal of the equivalent resistor. And we can generalize that to N, capital N resistors in parallel to give us 1 over R equivalent is this sum of reciprocals, 1 over R1 plus dot 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 up to 1 over R sub N. Anytime you have parallel resistors, you're thinking adding their reciprocals. And the reciprocal of ohms is conductance. And sometimes you might see this as G equivalent, where G is 1 over R equivalent is equal to the sum of the G's, where G1 is 1 over R1, G2 is 1 over R2. So now we would be summing conductances when these resistors are in parallel. Just another way of thinking of that same concept. Let's look at a special case. Suppose we had two resistors in parallel and we want to combine those into one equivalent resistor. Is there a formula that we can just quickly write down to make this equivalence happen? We already know what it looks like. We know 1 over R equivalent is equal to the sum of the reciprocals of the individual resistors that are in parallel. 1 over R1 plus 1 over R2. And if we now use our algebra skills, we can put those over a common denominator, R1 times R2, and that means that we have R2 plus R1. Maybe it's not real clear what R equivalent is from that expression, but we can always multiply by 1. And really what I'm wanting to do is I want to get a 1 in my numerator of the right-hand side. And I can get a 1 in the numerator by multiplying by 1 over R1 plus R2. But that's not allowed algebraically unless I do the same thing to the denominator. Which now leaves me with 1 over R equivalent is 1. That's what I wanted to end up in the numerator. The R1 plus R2 divided by R1 plus R2 gives me 1. And downstairs I have R1, R2 over the sum R1 plus R2. Or in fact, whoops, that should allow me to write then R equivalent is just what's in the denominator, which in this case is the product of those two parallel resistors divided by the sum of those two parallel resistors. Anytime you have two resistors in parallel, you can combine them into an equivalent resistor using this formula. You take the product of the two and divide by their sum. And that number is now an equivalent resistor that looks like the two in parallel. Let's look at a couple of examples of that. Suppose somebody now presents you with this. They have an R1 and then they have a second resistor, which in this case is just a bare wire, which is considered a short. So you should expect a particular answer for if I now hooked up a digital multimeter set on the ohm setting to measure ohms. If I measured the resistance from A to B, what should I see on that ohm meter? It better show me 0 ohms, right? Because now I'm really just measuring the resistance of a bare wire. Now, does the formula produce that result? We anticipate R sub AB. That's what that branched arrow represents. It's basically the impedance looking into terminals AB, or the resistance looking into AB. That's now, based on our formula, the first resistor times the resistance of the second resistor. What's the resistance of this? That's 0. And what does that give us? What we hoped. Now we have a product of 0 with a number divided by a valid number. We don't have 0 in the denominator that we're dividing by. We're dividing by a real number, R1. This is now 0 over R1, which is 0. And that's what we would have expected. Anytime you short out a resistor, you're basically removing it from the circuit. Example 2. What's the resistance looking into terminals AB from that interconnected mess of resistors? Can we find it? And now, essentially, what we're trying to do is maybe work from right to left to try to collapse that network down to something that looks like a single resistor. And I would like to argue that based on what you've learned today, we can accomplish that goal. Yes? Yes, so now the goal is anytime you see two resistors or more in series, combine those. And now if you see two resistors in parallel, combine those based on our parallel formula. And if you look, hopefully you immediately see that those two resistors combine to form a single equivalent resistor having what value? Just their sum, which is 20. Which now says that I have this 30. Do you see that 30 now is effectively in parallel with 20? So now I look over at what I have left, and I have 30 in parallel with 20. That's what's in the yellow highlight. And that, we said, can be the equivalent of that resistance of those two resistors in parallel can be formed by taking their product and dividing by their sum. Or how many nickels do you have if you have 60 cents in your pocket? You have 12 nickels. You guys don't carry nickels. You PayPal or whatever you do. You have all sorts of money in your pocket, but it's hard to count. Well, never mind. So there's 12. We now have at the, let me see if I can make this. Let me say that's nodes C and D. Is that okay? And at nodes C and D, we now have, we haven't done anything with the 8, but we've now collapsed a lot of that down to 12, and then between C and D, we have 5, and we have other stuff to the left of that, but for now this is what we're interested in. That's the thought process that we're working through. And now you know how to simplify this. You know that you can take those two and combine those in series to get 20. And now we have 5 in parallel with 20. And that's now the product of the two divided by their sum. Guess I'm going old school. How many quarters are in a dollar? That's what we have. We now have 4. So now that parallel combination of 5 and 20. And do you see that if you looked at the formula, you could deduce this, but if you combine two resistors in parallel, the net result better be smaller than either of those two, or smaller than the smallest resistor. In this case, we had a 5 and a 20 in parallel. We end up with a 4. What did we have before? We had a 30 and a 20 in parallel, and we ended up with 12. The parallel combination of two resistors is always less than the smallest of those two resistors in parallel. Something to keep in mind. If you make an algebra mistake and you end up with 40 for the parallel combination of 30 and 20, you go, whoops, something's wrong. Should be less than 20. And it's 12. Here it's 4. And now what do we have? If we go back, we now have, I'm going to cheat and use my notes here so I can see it and not keep scrolling. We have this 11, and now between C and D, we've simplified that to 4. And there's a 10, and here's a 12, and here's a 36. To get us to A and B. So if I call that node E, I think you know the drill. We now have 15 in parallel with 10. And that's going to be 10 times 15 all over their sum, or 25. Now we have 6 quarters in 150, or in $1.50. The parallel combination of 10 and 15 gives us 6. Now we end up with, and there's nothing wrong with drawing all of these out as you're working through the process. Now the equivalent resistance between A and B is going to be 36 in parallel with 18. I'm writing 36 as 2 times 18 because this, I didn't want to bring my calculator and have to calculate 18 squared, or 18 times 36. So this 18 cancels that, and now I have 2 over 3 times 18, or 12. So the equivalent resistor from that mess of a network before, whatever you applied to terminals A, B, it's effectively seeing 12 ohms. And we were able to collapse that down, working from right to left, to get to that net result, using parallel series combination of resistors. Let's talk about the next topic, which is voltage divider circuits. How would you start labeling this circuit based on the skills that you now possess in terms of KVL and KCL? And I guess I'm giving it away a little bit. If I want to write a KVL equation for this circuit, what voltages might I be interested in? Or how do I want to set this up to start analyzing or writing a KVL for this series connection of a voltage, V sub S, applied across 2 resistors that are in series? What you could do when you start looking at these circuits to begin with, you might just say, I'm not quite sure what I'm after. Let me just start labeling, and give yourself some time to get comfortable with what you have in front of you. Here, if you wrote a KVL equation, do you see that that would be minus V sub S plus V1 plus V2 is equal to 0? Just going around that KVL. And that particular label could be the current I through each of those circuit elements. It's a series combination. The current I is the same through all three elements. But here, we can solve for V sub s, and V sub s becomes V1 plus V sub 2. Or you can see then that this voltage that's superimposed across those two series resistors divides among the two resistors. One is a V1 and the other is a V2. And that's what we mean by voltage divider. The voltage, V sub s, is being divided between V sub 1, or the voltage across R1, and V sub 2, the voltage across R sub 2. That's a voltage division. We're dividing the original voltage, V sub s, in this case into two pieces, one across R1 and one across R2. Can we actually come up with an expression for V1 and or V2 in terms of R1, R2, and V sub s? In that simple configuration, can we now just write down what V1 is as a formula in terms of R1, R2, and V sub s? And if it doesn't immediately jump out at you, which it may not, we haven't yet learned it, let's derive it. If we write our KVL equation, that's minus V sub s plus R1I plus R sub 2I. Now I'm getting rid of the V1 and the V2 initially and trying to just solve for the one unknown, I, that exists in that particular circuit. Or the sum of those two resistors times I will give us V sub s. Or now we have a formula for the current. That's now, and you maybe already knew that based on what we talked about with series combinations of resistors. Oh, the equivalent resistance is just the sum of those two resistors. The current then is V divided by that equivalent resistor, R1 plus R2. What does that mean we have for V1? V1 is now R1I, but that's now R1 over R1 plus R sub 2 times V sub s. Using our formula for I and pulling out V sub s from 1 over R1 plus R2. And this now tells us, or provides us with, a formula for the voltage divided across that first resistor R1 in terms of that resistor R1 and the other resistor R2 and the total voltage V sub s. Do you see now that V1 is a fraction of V sub s? R1 is obviously less than R1 plus R2. R1 divided by R1 plus R2 is going to be a fraction, and that's the fraction of V sub s that's imposed across or exists across R1. That's the voltage divided across V1. We can do the same thing for V sub 2. And in these cases now, voltage is divided, and V1 and V sub 2 are fractions of the total voltage V sub s. let's step that up a notch. Suppose now that somebody says, I'm going to tweak it a little bit. I'm going to throw a third resistor in there. And maybe they say, what is V sub 2? What's that voltage? And can we come up with a formula for that? Could we do it by brute force? Well, let's put some numbers in. I already have a 10-volt source, right? Suppose that I now say R1 is 5, R2 is 2, and R3 is 3. I'm getting very creative with these values. Actually, the creativity was on R sub 1, that being 5. And maybe you can see why. Those resistors sum up to equal 10, and I'm going to be dividing that into 10, and I can do that math. 10 divided by 10 gives me 1, and now we know what the current is. Brute force, if we were wanting to know what V2 was, we could do a KVL. We'd say minus 10 plus R1 plus R2 plus R sub 3 times I is equal to 0. And this is 10. I is equal to 1 amp, so V sub 2 is R sub 2 I, which is now 2 volts. 2 times I, which is 2. But we can actually provide a general formula when we have this string of resistors a general divider formula. V sub m is now going to be R sub m over the sum of all of these R sub l's times V sub s, where this L is going from 1 to, in this case, it's 3. So that V sub 2 is 2 over 10 times 10, which was 2. V sub 1 R1 was 5. V1 becomes 5, and V sub 3, R3 was 3, and we end up with V sub 3 being 3. Obviously, I didn't know how much space to provide. But here's the caution that I want to at least make clear before we get too far into this. If I now said, what is V sub 2? What do you know that V sub 2 is not equal to? If I'm saying caution, caution, flashing red light in your rear view mirror, actually this needs to be in front of your screen on your front dash, this caution. If you now have this interconnected circuit and somebody says, what's V2? What you don't want to do, especially if they ask who you had 220 with, oh yeah, that was smart. Oh, and you got this wrong, really? R3 is loading R2, meaning you can't just apply the standard voltage divider formula, R2 over R1 plus R2 times V sub s, to get the answer. That's not the case. V sub 2 is not. So let me finish in red. Note, V sub 2 is not equal to R sub 2 over R1 plus R2 times V sub S. And we'll stop at that point, but maybe what I would ask you to do on your own, wow, I even forgot my scribbles to give me space. Try to find a formula for R sub, or for V sub 2 in this particular diagram. And if you're struggling, there's an example in the book, example 3.4 will walk you through that process. I'll see you tomorrow.